Okay, today we go back to the random variable rules, but this time we're going to take a look at a problem in context to see what those rules mean to a real world situation. So we're going to take a look at page 409 in the textbook number 36. It is a word problem. I'm not going to copy it down. You can look it up at your leisure if you want to go back and look at the details of that later. But we'll get the gist of it. A company selling vegetable seeds in packets of 20. So we're selling different kinds of seeds, packets of 20, little envelopes. Estimates that the mean number of seeds that will actually grow is 18. So we start off with a piece of information, and that's that the mean number of seeds that will actually grow, mu, is 18. So you get 20 in a package, on average 18 of them actually grow, with a standard deviation, that's sigma, of 1.2. You buy 5 different seed packets. So 5 different seed packets are bought. And we want to find in parts A and B how many good seeds we expect to get and the standard deviation. So we'll start with how many good seeds you can expect to get. Expect to get means it's an expected value. That's a mean. We can either do that as E of X or mu of X. Doesn't really matter. Of course, first we need to define what X is. So X is a random variable. Let's define what it means. X is about how many good seeds you get in a packet, because we know the summary statistics for that. We know 18 good seeds in a packet with a standard deviation of 1.2 is typical. So X, the random variable, has to be equal to the number of good seeds in one packet. That's all we have information for, is what typically happens in one packet. So we need to make sure we're clear that X represents a single packet of seeds, because that's all we have the summary statistics for. Which means as we go back up here, we're looking at mean of X equals 18 and sigma of X equals 1.2. So we're looking at some variable X with those summary statistics. And in part A, we want the expected value of the number of good seeds, or the mean, if you want to use a mu, of the number of good seeds in 5 packets. Oh, 5 packets, not 1. Okay. So we need to put 5 packets together. Let's try that again. E of, the temptation is to do 5 times X. That's not correct, because 5 times X implies that we have 1 packet and we're multiplying it by 5. We have 5 different packets. They could have different numbers of seeds in them, different numbers of good seeds in them. So we're going to need to use some subscripts, and do x sub 1 plus x plus 2, x sub 2 plus dot 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 plus x sub 5. And we can do the whole list. Once you get more than 3 or 4 of something, then ellipses are a good way to shorten your work a little bit. So we're looking for the expected value of the sum of those 5 seed packets, and the number of good seeds in those. We'll work down the page this time. Our random variable rules dictate that if we have the mean of a sum, that's equal to the sum of the means. So this is equal to E of x1 plus E of x2 plus dot 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 plus expected value of x sub 5. The mean of X is 18, so this is just 5 18s added together. So 18 plus dot 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 plus 18. In our calculator, the quickest thing to do is 5 times 18, and that's equal to 90. We actually have a context this time, so let's put our context back. So that means 90 good seeds can be expected if we buy 5 packets on average. Part B, we're looking for the standard deviation. So standard deviation of x1 plus x2 plus dot 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 plus x sub 5. Random variable rules apply to variances, not standard deviation. So we're going to rewrite that as the square root of the variance of x sub 1 plus x sub 2 plus dot 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 plus x sub 5. Variances add, so it's like an extension of the Pythagorean theorem. So we're going to split up those variances, so that's the square root of variance of x1 plus variance of x2 plus dot 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 plus variance of x sub 5. We know that the standard deviation of x is 1.2, so if we substitute, this is equal to the square root of 1.2 squared plus 1.2 squared plus dot 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 plus 1.2 squared. Now what we're going to want to do here is in our calculator, we're going to type square root of 5 times 1.2 squared. Repeated addition is multiplication. If we get a nice long list here, we're not going to want to type all those individual values in. So we'll just treat it like multiplication and then take the square root. So once we get that number crunched, we end up with 2.68 for our final result, and that is the standard deviation of the number of good seeds in one packet. Ultimately, what we want to do with this information later on is to then be able to look at a normal model that shows a distribution of all the good seed packets or good seeds in packets in the whole universe, and be able to say, find the probability that you get 5 seed packets that only have 25 good seeds total. That would be a very unusual event, and we can calculate the probability for that if our seed packages can be described by a normal model. So we're getting ready to take this business and connect it back to that model, and then we'll be ready to study some hypothesis testing soon. Last but not least on this problem, in part C, we are asked about what assumptions we need to make in order for this to work. And what we haven't really talked about yet was the fact that on that Detmer-Dogs worksheet, we had to assume that each of our variables was an independent event. So the choice of the size of the hot dog was independent of the choice of the size of the bun. The means don't really matter. Those work the same way whether you have independent variables or not. But the standard deviations are kind of tricky, because if you have independent random variables, these standard deviation rules, variance rules, work quite well. If you have some association between your variables, however, then this is messed up, because variation amongst similar packets is smaller than the variation amongst packets that are all independent. So we have to, in order to do the calculations for part B, we have to assume that each packet's good seeds is independent of all other packets. And that could be true, that could not be true. Part of this question is whether or not this is reasonable, whether this assumption is warranted. It kind of depends on the situation, which we don't really know. If your 5 seed packets come from different lots, let's say you bought a packet of tomato seed and a packet of pepper seed and a packet of cucumber seed, then there's a pretty good chance that this independence assumption is true and all is well. If you bought 5 packets of bean seed, all from the same lot, all from the same bin, and that bin just happened to have been exposed to maybe some additional moisture when it should not have been, then we might have a problem, because it turns out in that case those 5 packets of seeds have some relationship with each other, and you might have an unusually high number of bad seeds in those, and each one's number of good seeds no longer be independent. So the answer to part C is really a little more complicated. We don't know if we can assume this or not. We just kind of walk around hoping that it's true. And if it's not, then our calculations aren't really quite dependable anymore. Okay, so we're going to end there. You're going to do 3 or 4 examples. The sub's going to give you that assignment. My work is hanging over on the sideboard so that if you get stuck, you can go take a look. Work together, help each other, and we will get questions when I'm back tomorrow and move on from there. Have a good day, and I'll see you tomorrow.